Q over Q naught. Q Q naught. Q over Q naught. Still working. Still needs work. Still needs work. Still not good yet.
Have you found anyone?
Yeah, I got a couple of physiotherapists.
Hope to the house.
Yeah.
I'll see you later.
I'll see you soon. Testing. Okay, so the sound's working. Jitsi should be working. That Jitsi. Okay, so I've got my chat open, so let me know if you can hear me. Just type in the chat if you can hear me clearly once and only once, exactly once. Good. So I have all the microphones that are not going through the mixing console are all muted. And I've got my phone running a Jitsi with a muted microphone so I can hear in my earpiece what's actually being sent and received to close the feedback loop. And I've got a small number of microphones running through the mixing console. Hopefully that's clear. Sound. So one thing, apologies for the slow updates. We had the hard drive crash on the server, and so that just replacing that and recovering data and everything. And then shortly after that, the power went out to some of the buildings. There's a power surge that had some impact on some of the other systems. So we're just trying to recover that. So now I'm just trying to get things back to normal, whatever normal means, or if that's even possible. Should I say not use the word normal? I should say just getting things working nicely in some way or another. So we're moving through comparametric equations and into superposimetric equations. So we're moving forward with lab3. Give people a couple of minutes to join on. And if you have any questions or anything, I'll be on afterwards, right after the lecture. Be able to answer a few questions. So this will be something fun to think about over reading week. Writing week for us professors, because we're writing research papers. And you're all welcome to join us in writing some research papers if you like. If you want to see your name published in scientific literature, right, join us to write something that's fun and simple. So now, if we look at lab 3, I'm just in the midst of recovering lab3 data, so it's not all finished yet in the recovery process. But lab3 is quantographic sensing based on linearity and superposition, and I'm just in the midst of recovering some of this data that we'll use in lab3. So what we're going to do in lab3 is we're going to combine two pictures. We're going to combine two differently illuminated images, two pictures that were taken under different lighting. We're going to combine them together, and we're going to compare them with a picture that we took with both of those two lights on together. And we're going to try to adjust the response function of the composition to minimize the error between the synthetic view of the two images and the actual data that was collected. So that's part A of the lab, is to understand how a law of composition on images, to combine images together with a simple law of composition pixel-wise. And you can either use the computer-enhanced multiple exposure numerical technique Cement if you wish. You can download it and modify the code. Very sloppy, badly written code, thrown together quickly. Or you can write your own code, which I would actually suggest. And it's fairly simple law of composition. Now, to compose two images together, you're going to read in two data arrays and then find a simple law of composition to combine them in such a way that you would get the same thing as if you did a multiple exposure in part A of the lab. Now, part B of the lab is augmented reality overlays. So in part B, what we're going to do is combine two images together. And so the example I've got here is this oscillograph, and an oscillograph is a photograph from an oscilloscope screen, like this one over here, actually, this HP 1200A cathode ray oscilloscope. And that's my heart monitor, or at least that's what I was using to read out, to see my heart waveform. And so we're going to overlay that on top of the field of view, on top of my video stream from my eyeglasses. So we're also going to overlay my heart rate. So we're going to take that data and we're going to measure how quickly it goes from peak to peak. In this case, it's 72 beats per minute at this moment. We're going to combine that together and overlay that. And that's exactly what we did with the eyeglasses that I typically have. Right here, I've just got in my swim bag here the eyeglasses that I take with me when I do my daily swim. And that's exactly what we have happening here. So I've got in this case, I've got a simple OH1 heart monitor, and what we did is we made a little overlay on here so that while I swim, I can see what my heart is. The waveform is overlaid, and then there's also the heart rate is overlaid, and that gives us the ability to see this augmented reality overlay when we're in running. You know, when you run, the heart rate increases, and then when you go for a swim, it gets less. My resting heart rate's around 45 beats per minute or so, but it's possible when you swim in ice water, immerse yourself in ice water, to get it down into the 30s. Get yourself calmed down. If you're an inexperienced swimmer, when you jump into ice water, you may panic and your heart rate will go racing, but if you're able to calm yourself, look at your heart rate and bring it down, then you're able to experience a state of calm. So this is very useful to have biofeedback to understand the world around us and to be able to attain a state of calm and mindfulness. And this is kind of the basis of the other company that we founded called Interaxon, which makes a product called the Muse, which is about mindfulness and meditation, We have the Muse S, which is the sleep band, a sleep lab that you wear on your head. So all these things are perfect for understanding, seeing and understanding mindfulness and how to be able to get yourself into a mindful state. And so biofeedback of this sort is quite instrumental. So we'll learn simply how to do this with the eyeglass. So the eyeglass has a video feed, and the typical ITAP collects video of the surroundings and modifies it and then presents it to the wearer. It's called mediated reality, or what we called XR, X-reality, extended reality. That was a term Charles Wyckoff and I coined in 1991. So XR is what we would be using here to take this photograph of the cathode ray oscillograph or oscilloscope screen, and also the display of the heart rate. Now what I have here is using Nixie photographs. So what the nicest kind of looking traditional heart monitor, I think, is to photograph each of the Nixie numerals from 0 to 9, and then to use those photographs as overlays, select the appropriate photograph. So you need a 7 and a 2, and we superimpose a photograph of a 7 from a Nixie indicating 2, and a photograph of the numeral 2. So for example, and then that can be overlaid. So that 72 can be overlaid. And so here's what it looks like. This is what you might expect to see when you finish your consolidation. So I've got the heart waveform showing in green, which is traditionally the color of a cathode ray oscillograph. And then I've got the heart rate shown in these Nixie numerals. So now we can ask the same question: what is the law of composition to combine these two images? Just like we did for part A, we took two photographs. We take one photograph with one light turned on, take another photograph with a second light turned on, take a third photograph with both of those lights turned on together, and then figure out how to combine the first two photographs to get the same as what you have in the third photograph. What you'll find is if you just add the first two photographs together, it looks a lot different than what's in the third photograph. So typically the image might go from 0 to 255, and both of them, and then when you add them together, it'll go from 0 to 511. And then what are you going to do? Clip it or scale it? And of course, whatever you do, it's not going to look like the second image very much. Now, if you took these pixels, you just say, if you did something really simple, just going to go to picture in picture here. I'll just put it in the upper right there. And then let me know, make sure you can hear me well. I think that sound should be showing up. So what you'll want to do is take these images and combine them somehow. You'll have an array of images. And this might be 0, 1, 2, 3, 0, 1 or something like that. And maybe this will be. And you'll combine them. And if you just add them, add this one to this one, and so it's going to be element by element. So the upper left-hand pixel in the destination is going to come from the upper left-hand pixel in the source of 1 and the upper left-hand pixel in the source of 2. So diagrammatically, this pixel here and this pixel here are going to go into some kind of combiner, and that combiner is going to put the result right there. And then the next pixel over and the next pixel over here are going to also get combined into this result here. And then likewise the next pixel here and the next pixel here over are going to somehow get combined and go over here, and so on. And then we're going to go all the way along to the end here. The upper right pixel of this image and the upper right pixel of this image are going to somehow get combined to make the upper right of this one. And then we're going to start in the second row of the image, and here also. And then these two are going to get combined into this image array. So we'll have a two-dimensional array of images, and we'll just combine them together into another two-dimensional array here. Now, if we were to just hazard a guess, something quick and simple, if I had to say a really, really quick and simple function that would combine these two images, so I want you just to add the two images together, and then maybe you'll rescale it, and then maybe you'll clip it. There's two possibilities. One is to rescale it, other is to clip, and there's lots of other possibilities too, but those are the simplest that come to mind. Now, a better approach is to take these two images take your source image and go through some function f inverse and try to get an estimate of Q, and then add them and then go through F again into your final result. Now, a pretty good estimate of F, if you don't know anything, if you just want to randomly pick a function, if we chose F, if we thought it was a square root function, then that's a kind of a quick guess of what the response function might be, because generally the response function is somewhat compressive. It's sort of shaped like this. If this is Q and this is F, generally the response function will be concave down like this. In other words, as you increase the amount of light, the output starts to increase quite a bit initially, but then as you get more and more light in, it levels off. And that's consistent with the way that most television screens traditionally have displayed images, as well as photographic media. Television screens tend to display images compressively. So what you typically have is the camera has a dynamic range compressor in it. So you've got your camera like this, and inside that camera there's a sensor array that then goes to a dynamic range compressor. It compresses that dynamic range, and then it outputs that signal to the outside world, because we like to see things compressed. There's, logarithm is a possible compressor. There's simple kinds of compressors like a log function or a square root function or some kind of root that's not necessarily a square root, but it might be Q to some constant, for example. And so if we're trying to get at this, we want to expand this. So we want to first expand the dynamic range. And then, in general, process. And then compress the dynamic range. And so you can see here that there's we call this anti-homomorphic filtering. Now, Stockham, a professor at MIT, proposed the idea of homomorphic filtering. So you can search that up, this concept of homomorphic filtering from Stockham. And he said that what we need to do is to take the output of the camera and take its logarithm, for example, and then do processing on it, and then take the anti-log. That is to say, take the output of the camera and then compress the dynamic range, do processing, and then uncompress it. And his argument was, you know, around human perception and everything. But what I said to him was that, wait a minute, that's wrong, because cameras already have dynamic range compression built into them. And so what you're saying is we should just process that signal. Why compress it when it's already compressed? And I said we should do the exact opposite of what Stockham proposed. We should take the camera signal, expand it first, then process it, and then compress the dynamic range, and finally come to the output here. So I said what we should do is do the exact opposite of what you're advocating. And I guess a lot of people don't like me too much because I tend to be contrarian sometimes. But sometimes you have to say things, and some people are willing to accept criticism and actually enter into debate. That's one thing I did like about MIT, is people there are often willing to enter into debate with things they don't necessarily agree with initially. So anyway, here we have a very simple thing. What's the simplest example of a dynamic range expander you can think of? Well, that would be just the square function. So if this is f right here, well, I'll call that v here, let's say, just for fun. That's a voltage v, let's say, coming in. We're going to expand it. We take v squared, and then we're going to process it. And so then that's going to be some processed function p of v squared, say. And then we're going to compress it. Actually, I should just draw this where it actually is. Say that's v squared. P of v squared. Going to be right here. And then at the output, we're going to have the square root p of v squared. And so that's our anti-homomorphic processing. And so that's just using a very simple example of a square function, because that's super simple. Okay, so now implicit here is a really simple example. If I said that, well, here's a parametric equation for you. Suppose I told you that there was f and that there was g, and I told you that g was the square root of 2 times f. So say f was 0, I'll make some numbers in here, 1, 2, 3, 4, 5, 6, 7, 8, let's say. And then over here, I'm just going to have the root 2 times that. So this will be 0. This will be the square root of 2, 2 root 2, 3 root 2. So this is just root 2 times more. And so if this was to be seen comparametrically, we'd have a simple graph, comparagraph. You all remember what a comparagraph is. That's a comparagraph. And in the comparagraph, we have here paragraphically that this is just a straight line. Now, if it was a unity slopes here, roughly, or these graph lines kind of straight like this, and then what we're going to have is something that's a little bit steeper than that. So it's going to be right about here, 1.4, let's say roughly 2.8 about here, and so on. So in this simple example, we're going to have, now this is F and G, 2 consecutive letters of the alphabet. It's just like an XY plot, but with F and G instead of X and Y. And remember, this is a function and this is a function. Both of these are functions. And so now the slope here G over F is the square root of 2, i.e. G root 2F now we know, of course, if we know kind of from our own experience that if F equals root Q, then G equals root 2Q, which is equal to root 2 root Q actually I think I'm writing off the end of the board here. G equals root 2Q, which is equal to root 2 root Q, which is equal to root 2F, which is exactly this. So then, of course, we know the solution to this comparametric equation is, in fact, so if F equals root Q, we square both sides, then F squared equals Q. So now Q is equal to F squared, but it's relative. So remember, we don't know what it is. So we know that we're going to say that Q over Q0, some arbitrary unknown that we don't necessarily know just yet. We know that Q over Q0 is going to be this squared because Q equals F squared. So Q over Q0 is the square of that. So this is going to be, I'm going to square that, 1, square this, 4, 9, 16, 25, 36, 49, 64, so on. Now this is q over q0, and then if we put 2q over q0 in this column, we're just simply going to double that and then twice this. And so now, again, we can see the pattern that we get if we unwrap or unravel this. And so, again, apologies for the delay in getting content recovered and getting our system back up and running again, but I'm slowly uploading some new lectures, other material, and recovering some of the older original material. So now we have a simple law of composition that I can propose. The very, very simplest law of composition is just to use this, which is kind of reasonable. So if I simply take two images, this image and this image, and I consider, say, the upper left-hand corner pixel of this image and this image, and I simply, let's say this is V1, this is V2, is this array, where V is going to be F. V1 is approximately an instance of F of Q. V2 is approximately an instance of F of 2Q in the comparametrics case, but in this case was differently illuminated images. It's not necessarily that one is related to the other in that way, but we can still use this law of composition here. So now if I take this image and I take V1, let's say that's 0, 0, or whatever it is, say X 0, Y 0, whatever it is, and then here I'll have V2 of X 0, Y 0, whatever that coordinate is. It could be some arbitrary position. Say X0, Y0, some arbitrary point P, and it's important that we're at exactly the same point in the second image. So that's also the same pair of coordinates. And then we got these two inputs, and what we're going to say, I'll say this vectorially, that what we want to do is say V3, which is our combined, is going to be constructed, or it's approximately, we want to see to what extent it differs from the square root V1 squared plus V2 squared. So we take whatever pixel value is here and square it, and add it to the square of this pixel value, and then take the square root. Now this is called a norm or a distance. This is a familiar Euclidean norm, Euclidean distance, because if we think of image 1, say V1 is right here, V2 is right here, then we're going to take the square root of the sum of the squares. So if V1 is some amount here, V2, we're going to take whatever that is. The result is going to be the distance from the origin. So that's R, radius. Say R equals square root of V1 squared plus V2 squared. R is the radius, it's the distance. So the pixel value that you get coming out of this law of composition is just the Euclidean norm of the distance in light space, or in image space, really. So you're taking that square root of the sum of the squares. Now, more generally, a norm is calculated as, we could say, V3 is going to be compared with some norm, say P. The pth root might not be 2 of this V1 to the P plus V2 to the P, and that's a particular norm. For P equals 2, that's the familiar Euclidean norm. Now what we can do is try different numbers here, and you can just look at how these images look. So you've got your two images here. Say this is V1. This is a picture that you took with one of the light sources turned on. This is V2. This will be a picture you took with the other light sources turned on. And I suggest you try a whole bunch of different examples. Mount your camera somehow so that it doesn't move. You can prop it over the edge of a table, you know, like I showed in the video. If you put your camera somewhere and you want it not to move, you might have like a smartphone. Like this, and you prop it up over the edge of a table or something like that, looking down at the floor underneath it. And so it's going to sit here, and then you have some objects down here underneath the camera. So I'll just kind of draw how you're going to do this in a really simple way. Make sure the table's really solid and this doesn't move at all between exposures. You're going to have, I draw this setup that you're going to have for lab 3. You're going to have a smartphone like this, let's say. And you want to set it to manual if you can. If you have a manual settings on the smartphone, that'll help. Set it to manual so it doesn't change exposures during the changing of the light. Get it sitting here like this. So this might be a table here. And then you might have your phone hanging off the edge of the table like this. And then what you have is objects down here on the floor. And you're going to have a couple of light sources. Say this is L1, lat 1, and you might have another light over here like this, L2, and you're going to turn on one light and take a picture. You can turn that light off and turn on the second light and take another picture, and then you're going to turn on both lights and take a third picture. And what we're trying to do is understand the relationship between the one picture and the other picture, and the result was both lights turned on. And so that relationship between these sets of images is really a whole bunch of equations, because each image is about, you know, like my camera has 108 megapixels in it, so it's about 108 million, more than 100 million data points when I take a picture. So if I've got these two images here, we have this situation here where they're getting combined, and then we're comparing. And then this allows us to try to recover the response function by looking at more than 1 million equations and only one unknown. So it's highly overdetermined, and thus we should be able to get an accurate estimate of that one unknown, which is P. Now, if you want to be more adventurous, and I welcome you to do this, because I'm always delighted when people do a little bit more than what's required in the lab. And I'm happy to award more than 100% bonus points, you know. And so that you can do really well in this course by doing something really fun and learning something and showing that you've learned something. But really, if you say, what is the response function of the camera? Say this is Q, and this is F, and I want to know what the response function is. It might not exactly be a square root function, but you could think of it as a lookup table for every number of pixel that it outputs. And let's say we just convert the images to black and white, convert them to grayscale to keep it simple, and then we could consider color later on. But let's start with something really simple, like just grayscale image. And really, really simple. And in that case, the image is just a lookup table. So for each f of q, there's 256 of them. You can think of it as a table when f of q is 0, 1, 2, 3, all the way to 255. For every number that the camera outputs, there's a certain quantity of light. Say this is the quantity. This is Q here. Or you could say it's Q over Q0 if you like. And so we have a lookup table, we have a construct. So what we want to know is we want to know what this is. So we could say really there's 256 unknowns here. So now here's an interesting proposition for you. Given 256 unknowns in maybe 100 million or more equations, can we determine those 256 unknowns? And the answer is quite simply yes. You know, that's very simple. We can determine those 256 unknowns and actually determine the true response function of the camera. So that's a nice little project, and if anyone wants to do that, we'll work on that. Be happy to help you write some papers, publish some results, get some of your work in scientific literature. But for the purpose of the lab is actually very easy. And I've done it very easy so that everybody in the class can do it without too much effort and learn at least learn conceptually what's happening. But for those who want to do a little bit of extra to have fun, like consider 256 unknowns instead of just one unknown. Anyway, with just the one unknown, we're going to take this, you know, v2 to the p, v1 to the p, and then we're going to combine them, pth root, and out's going to come something. And what we're going to do is take a look at what comes out, and for every p-value, we're going to try and find the p-value that gives the closest match between these two differently illuminated images and the picture that was taken with pulse lights on. And you can do that as a simple gradient optimized search. Or sometimes what people do is just try a whole bunch of different p-values and see which one gives the lowest number. Or you can even just plot a graph of error. So error, say the squared error you might even consider is the sum over all xy of the absolute value of v3 xy minus, actually I might even put v1 plus, I'll put this first because it'll be simple, v1 of xy plus v2 of xy minus v3 of xy. And if you take that absolute value over in that error and plot that out, this thing here, what you'll notice is that it comes down to a lowest value. There's a certain p-value where it's lowest. And traditionally, most old school video cameras were around 2.22. That was sort of the value of p that was typical of the old world. Nowadays, of course, you know, there's all kinds of different cameras with different kinds of aesthetic and so on. But you'll find something that is the minimum error. Another question you could ask is more aesthetic, from an artistic point of view. Which p-value gives the most pleasing result to the eye? You could ask that. You could say, well, if I just have p equals 1, it looks pretty awful. And if I have p equals infinity, by the way, everybody probably knows what these means. Like when p is 1, that's just the average. The p1 norm is the average. And when p equals infinity, it's the maximum. So a couple of simple extreme cases are just average the two images or add and clip. You really want to probably add and clip because you don't want to scale them back down because you want to get more light. It should actually get brighter when you have more light, so there should be more output. So you probably want to just add them and then clip them with a simple function like this that's linear, and then it goes straight off at 255. So add them and then take anything above 255 and bring it back down to 255. So that's your simplest law of composition. And then the other extreme of infinity is to simply take the maximum. So if you, in the limit, v1, v2 to the p, and v1 to the p, pth root, in the limit, as p approaches infinity, of this operation tends towards a max val function, where you just simply take the maximum, take the upper left pixel of this image, take the upper left pixel of that image, and choose whichever is bigger and output that. And so on, and go through the whole pair of images like that, and take a resulting image that represents the maximum value of each of the input images. Now, neither of those looks good. Neither of those looks good aesthetically. In particular, when you average them, or when you just add them together, it doesn't look natural. And when you take the infinity norm, you're going to get a sudden transition where you get a bright area. It also looks quite unnatural. But somewhere in between is a nice looking image. So you'll find sort of that values of 2, 3, 4, 5, something like that. Those numbers all look reasonable aesthetically, and you can make that artistic decision and try a bunch of examples. Take a bunch of different pictures like that, and you can even have some fun with different colored lights and stuff like that, and have some fun. Make this lab be fun. Take multiple exposures, combine them together, and have some fun. We often do that. You take a picture. It's fun to jump off a bridge or something like that into the lake, and then take all those pictures and combine them together where you're standing on the bridge and jumping down into the lake, and you can see yourself at multiple positions, and it's kind of a quadratic expression, as the acceleration due to gravity. You see these, you're here, 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 and then further and further apart as you drop down into the lake. And so that you can have a lot of fun artistically and visually combining images. And we call this law of composition the computer enhanced multiple exposure numerical technique called cement. Cement stands for computer enhanced multiple exposure numerical technique, and we cement the images together. We say we're going to cement the images together. And so you can download my version of Cement, and it's just a simple C program, bunch of C programs. And there's also a shell script called trowel.pl, which is a tool for applying Cement. It's a Perl script that calls Cement and combines the images together, and you give it a list of images. It's like v1.jpg or whatever, v2, say like this. And then you give it coefficients like RGB values 111, 111. So that just combines them together, cements them together, by the law of composition. It just simply takes F inverse of each of these images, adds them all up with these weights, and then applies F again. So it's going to take all of these input images, and you can do multiple images, as many as you want, sort of within reason, I guess. Take all these different images, and then you simply apply F inverse to each one, and then you multiply it by the weight, which is RGB values, and then add them all up, and then apply F again to get the result. And so these RGB values, if you just put 111, 111, 111, so you take a whole bunch of pictures and generate a text file and just put 111 after each name and then run trowel on that, it'll cement them together with a weight of 111. And of course you can change these weights if you want. So you can add different numbers, experiment with the RGB values, so you can have the effect as if you had colored lights. So you can take a picture, if you do something like this with two images, 100 and then 001 for the second one, the picture will look the same as if you had a red light bulb for lamp 1 and a blue light bulb for lamp 2, as if those lamps were colored even though they were just white lights in reality. So have fun and experiment with cement, learn how it works, learn about comparametrics. I'm going to post some more comparametrics lecture material, so you really understand comparametrics thoroughly before moving on to superposimetrics. And the big thing is I hope you have fun, and then when you're finished doing that just combining some images together simply in part A of the lab, part B is where it's going to really get fun, because now you're doing augmented reality overlays and you're doing this whole idea of extended reality, XR, and how can you envision the eyeglass of the future where you have XR eyeglasses that extend your capacity in reality. And feel free to sign up one of these smart swims if you want to try and implement something on that. Try some overlays and join us for a swim in the lake and try and overlay some heart data with an OH1 heart monitor or any of your favorite underwater heart monitors, or go for a run and overlay your heart waveform while you're jogging. Feel free to sign out one of the Vuzix Blade eyeglasses. They don't work underwater, of course, they're just for use on land. But you can go for a run or a jog or exercise or do some biofeedback and look at this overlay on top of the screen and kind of get a really nice idea. Instead of just dropping it on with computer graphics on top, there's something visually, artistically beautiful about overlaying it in such a way that looks like it was actually a multiple exposure rather than just sticking it on top. Even if you blend it with an alpha channel, your law of composition is just addition. And I think most of the people working in augmented reality don't understand superposimetrics that well, because most of these reality things look like garbage, kind of. They're just stuck on top or added with an alpha channel or something like that without regard to the natural response function of the recording and capture media. But anyway, knowing what you know, you'll be at the forefront of all this and be able to really push the frontier of human endeavor in all of these directions. So now let me bring it back here and go off of picture-in-picture for a second. Let's go back to main camera. So I hope this has been lots of fun, and let me know if you have any questions. I'll stick around for a while to answer questions. And if there's anything you want to do that's fun, if you want to join on one of our fun research projects, write a research paper together. We got a paper deadline for March next month. And we're doing the Water HCI, Water Human Computer Interface Conference. So we're going to do it in March so that it falls in the school year. Traditionally, we used to do it in August over the last 24 years or so. And then last year we did it in December to include some of the winter swim events and stuff like that with the Vuzix Smart Swim and the underwater extended reality and all that sort of stuff. And this year we're going to try and do it in March so that it kind of lands inside the school year before April, when the school year winds down. So this will give you all a chance to kind of participate and join in. Okay, so I'll hang in there for any questions people might have.